We're going to talk about multiplication of polynomials today. The next time we're going to talk about factoring polynomials, which is basically undoing what we're learning how to do today. Just the same way like when you learn multiplication of numbers, right? We learn how to multiply them first, and then much later on, we learn how to divide them because one is harder than the other. But what's nice is that the more multiplication you do, the better you understand the division part. So similarly with multiplication of polynomials, the more of those that you've seen, the easier it will be to undo that or to factor them. So we're going to spend some time talking about that today. And first, but before we do that, I'm going to do something that's you're going to be like, dude, I saw this like 5 years ago. I don't need to do this again. Yes, we do. We're going to do it again. So here we go. I really, really want to make us believe what we're about to do. And I want to see why we're doing what we're about to do. What is 3 times 6?
18.
Are you sure?
Yes.
Okay. I believe you. I think you're right there. 3 times 6 should be 18. And we could think about this as saying, well, if I had 6 things, 1, 2, 3, 4, 5, 6, and I had 3 times as many, it would be like taking those 6 things and making 3 copies of them, right? That's what multiplication means, right? In other words, I have 3 things here, or 3 rows here and 6 columns of things there. I would have a total of 1, 2, 3, 4, 5, 18 of them. That's what that means. Now, what is 3 times, oh, I don't know, 2 plus 4?
18.
Are you sure?
Yes.
It has to be, right? Because I haven't changed that number. It looks different than it originally was, but it's the same number. And so if math is going to be consistent, I have to get the same thing. This should still be 18, right? And we can see this in a different way, actually. This is like saying, well, all you've done here is you've split up the 2 and the 4. You said you have 2 things and you have 4 things, and then you're going to take that quantity and do it 3 times. So you should have this type of thing right here. We would have the 2's replicated 3 times. We would have the 4's replicated 3 times. And we have then the number 3 times 2 plus 4, right? We have 3 times 2 things, and we're adding that to 3 times 4 things. And so basically, yes, this has to be that right there. And in pictures, what we've just basically discovered is what's called the distributive property of multiplication over subtraction.
Mm-hmm.
Why they call it over subtraction, I don't know, because maybe it takes precedence over it. But basically what we have to do, what I like to think about is that the 3 jumps over the plus sign. So the multiplication goes over anyway. So, and we could see that in order for this to be consistent, we have to take that and multiply him by everything that's in there. We can't leave one of them out, right? Because when we do this, we get 3 times 2 is what?
6.
6. And what is 3 times 4?
12.
And when you add those together, oh, lo and behold, you get 18. And in pictures, that's all we've done right here. We took 3 times 2, then we took 3 times 4, and boom, it does give me 6 and 12. Add those together, you do get 18. So it has to be that way. We can't stop short, right? And like, I've seen this a billion times. I doubt that you'd fall into this trap, but it's funny how people do when you start doing something different than numbers. When you start to put symbols in here, like X's and Y's and stuff like that, people, for some reason, forget that this has to be true. That you have to multiply it into both of them. And they do something like this. And they say, okay, well, I'll just distribute it into the first one and then forget about the rest. And when you do that, you end up with 6 plus 4, which is only 10. And that's not this. And that's not, and that is, well, that is not the original guy right there. Okay. So almost done. I want to do a couple more. So we are certain that 3 times 2 plus 4 is still equal to 18. That has not changed anything. Okay. What is that?
18.
Are you sure?
Yeah.
It had better be, right? And I'm going to do one more picture because I love pictures, right? What we're doing here is we're saying, we're basically, now we're just splitting this up again. We're saying instead of 3 here, you have 1 and you have 2. So you have 1 times that first quantity. So 1 times the 1, the 2, and the 4. And then you have 2 times the second quantity, right? And you end up with this kind of picture here. Right? So I just took my original 18 things, and now I'm just splitting them up in different ways. In this case, we have 1 of these and 2 of these, which is the same thing as 3. And then we have 2 of these and 4 of these, which is the same thing as 6. It's just I've split them up differently, but I have the same number of things as I started with, right?
Mm-hmm.
Now, what we just said, right, is that the 3 distributes over and hits the 2. The 3 jumps over, hits the 4. Well, then the same thing has to be true when 3 is written as 1 plus 2. In other words, the entire thing, 1 plus 2 jumps over twice. And we get 1 plus 2 times 2 plus 1 plus 2 times 4. But then we see, well, wait a minute, this is the same principle, right? This is 2 times that. And so I have to distribute him into there. And so I get 1 times 2 plus 2 times 2 plus distribute him into there. 1 times 4 plus 2 times 4. And in pictures, right, that's kind of exactly what we did here. We have 1 times 2. Yep. 2 times 2. Yep. The 1 times 4, which is right there, and the 2 times 4, which is right there. All together, that gives me 2 plus 4 plus 4 plus 8, which by pictures is the exact same thing as that. And so I agree with you. Yes, fat guy's still equal to 18. Now, the thing is, and this is where we're going to start getting. So this has all been review, and you're like, I know, right? But this is where we're going to start getting into our topic for today, is that doing this, like taking this and distributing it in, is kind of a pain. And when we start using bigger numbers, that's going to be even more of a pain. And so bigger numbers. When we start using more terms than just 2 and 2, it's going to be even more of a pain. So, for instance, this is the last one, I promise, and we're going to move on. 1 plus 2 plus 3. What's that times that?
18.
It should still be 18. It had better still be 18. Now you can kind of see, like, I could, if I were so inclined, say, okay, I'm going to distribute that into there, and I'll have my 1 plus 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3. And then I'll have to distribute again. 1 times 1 plus 2. And yeah. That it starts to get, it starts to, we have diminishing returns on this method. And I'm sorry, I did want to write this out. But I just want to do this real quick. 1 plus 2 times 3. So what would we have to do? Well, we'd have to take the 1 times the 1 plus the 2 times the 1 plus the 1 times the 2 plus the 2 times the 2 plus the 1 times the 3, and finally plus the 2 times the 3. The thing to notice here is that we have 1, 2, 3, 4, 5, 6 terms. And that's exactly how many ways you would pair this off. And so what in this scenario where we have 2 terms times something with 3 terms, what I like to do is I do what I call it double distribution, because you can see that's kind of what happens, right? This gets distributed into each of those, but then every one of those gets distributed into every one of these. In other words, every single term that ends up here does get multiplied by the first term, right? So in other words, that one ends up going into each one of these. And so we distribute the 1 into each one. Ditto with the 2, right? When we do our final bit, it's like that this second one gets distributed into the 1. The second one gets distributed into the 2. The second one gets distributed into the 3. It's the same thing as if we had done this. And that, when they're bigger like this, that's how I like to think about this. And so if I were to actually compute this, well, if I were to actually compute this, I'd say that's the same thing as 3 times 6, which we know is 18. But if they weren't numbers, right, I would say, well, we have to do all 6 of these multiplications. And so I would just go, okay, I'm going to distribute the top one first. That's a 1 times 1 is a 1. 1 times 2 is a 2. The 1 times 3 is a 3. Then I'm going to say, okay, the 2 times the 1 is a 2. And the 2 times a 2 is a 4. And the 2 times a 3 is a 6. And then I just add all those guys up and I get 1 plus 4 plus 7 plus 6, which I'm not even going to check. I'm sure comes out to 18. But that's a better way of using this principle that every single number needs to distribute into every other single number. Are we good?
Yes.
Okay, yeah. And like I said, this is, as of right now, this is just review, but I want to make sure that what we're about to do is on solid ground. I don't want it to just be a rule. I want to see that it has to be this way. And if we miss out on any of these multiplications along the way, then this will not add up to that. And that's why we have to do what we're doing. So, okay. Now, you've probably heard of FOIL. What's FOIL?
Oh,
It's an acronym.
yeah, I forget what it stands for.
Okay, okay, good. And this is the way, like I said, we do this double distribution thing. So this one needs to distribute into both of these, and this one needs to distribute into both of these. And I would normally, when they're bigger, I would do that in that order. But this has been ingrained in my brain so much that this is how I think about it. This is first,
Outside, inside, last. Okay.
And so basically, this is just a mnemonic device for how to go about doing this. And the way we do it is we say, okay, I'm going to multiply the first 2 together. So these 2 are first, and I would say, okay, just like with the 1 and the 1, right? We say 1 times 1. In this case, they're different numbers, and we don't know what they are. So it's an x times w, okay, xw. Outside, now they mean the outermost ones, right? So this guy and this guy are my outside. And so I get an x times z. The inside are these guys right here, the innermost ones, in this case, y times w. And then last are these guys, y and z. And what's nice about doing it this way in that order is that when they are similar polynomials, so let's say something like 2x plus y and I don't know, x plus 3y. Doing it in this order actually helps you keep things in, you'll see. So first gives me what? What's that times that?
Hold on.
Say again?
3x.
Wait a
Right.
minute. What is that times that?
Oh, 2x times x.
So we
Is-
write that as what? 2x times x is how many x's altogether? How do we write x times x?
Oh, x squared.
X squared. There you go. Okay. So, okay. Okay, so what is the outside?
2x times 3y.
Yeah, 2x times 3y. Now, what can we do with the, we could do multiplication in any order that we want, right?
Well,
So how about I bring all the constants out front to give
Okay.
me something like that? And I could rewrite that as what?
6xy.
6xy. And in practice, that's kind of what you're going to do. You're going to look at the coefficients first. And this is as I was, if I were going to do this one, what would go through my brain is, okay, first 2x and x squared, okay, 2x squared. Outer 2 and a 3 make 6. X times a y is an xy, just like that. Okay, so usually we just compute the coefficients first and then jumble all of those variables together. Now, what about inner for this guy? What's the inner product?
Yx.
Yx. And in practice, because of this commutative property of multiplication, we could do it in either order. And by convention, when x shows up first and y shows up second, that's how we keep things. And
Okay.
usually, just by convention, you go in the order of the alphabetical order, right?
Okay.
And so that's what we're going to do. We're going to keep, since x comes before y, whenever we write these guys down, we're going to put the x before the y. So we get plus another xy. So this was just to make sure we're on the same page. That was from my first. This one was from my outer. This one was from my inner. Now, what's my last?
3y squared.
3y squared. Now we kind of see what's nice about doing it in this order, why we don't just blindly double distribute and then double distribute the other way, is that now the stuff that's on the inside, well, we can combine those, can't we? Right? That's 6xy's plus an additional xy gives me how many xy's?
7xy.
7xy. And so 2x squared plus 7xy plus 3y squared would be my answer right there. You'll notice something that's nice about this is that since we've kept this guy in order, the same order as that guy, what we end up with is this term has an x squared, this term has an x to the first, this term has an x to the 0. So the x's are in descending order. The y's are in ascending order. They're in the exact opposite. This is, we could think about that as y to the 0. This is y to the 1, and this guy is y to the 2. And so it's kind of nice because it already, to do it in this order, already puts it in an order that we're going to want it in anyway. Like that is, it's very nice to have that. Okay, does that make some sense?
Yes.
Okay, let's try another here. And I want to just do, I'm going to throw a wrench in here, a couple of wrenches, actually. We're going to do this.
Great.
We're going to say x squared plus 3y. And then we're going to do, how about x minus 2y to the third. Okay, now there's a minus sign. Uh-oh. Uh-oh. Actually, yeah. Okay, yeah, we'll just do this one because you're going to see ones. Well, we'll just do it. So first, what do I get from my first multiplication?
X to the third.
X to the third, exactly. And what goes through my brain as I see this is, I remember that that means, oh, I have two X's, and then I'm multiplying that by one additional X. And so I have a total of three X's, which I could write simply as just saying X to the third. So we have X to the third. What about my outside? What do I get?
Negative. No, it would be a -2.
-2, yep.
X to the second, y to the third.
Yes, good. And you said it the way I think about it, right? Is let's look at the coefficients. I have a 1 here times a -2 right there. 1 times -2 gives me -2. So that's the first thing I write as I'm doing these. Then I'm going to look at the variables and say, okay, we have an x squared and well, those don't combine. I guess it's just a x squared and a y to the third. Nice. Okay. Okay, what do I get from my inner multiplication?
That's 3xy.
3xy, and you went ahead and did it in the order that we like. Good job. Now, finally, what's my last?
-6.
-6.
Y to the fourth.
Y to the fourth. There we go. Looks good. Now, you'll notice, like I said before, well, in one case, we do have a descending x's. We have x cubed, x squared, x, and then x to the 0. The y's are a little bit off, right? So just, that's okay. Like, that could happen. It's just that when they both, and what was different about the other one was they both had the same powers in both of them. So like, this happened to be x to the 1. That one was also x to the 1. What was over here was y to the 1. This one happened also to be y to the 1. So we would see the ascending and descending powers. We're going to see that whenever that's the case. Whenever this, like if this were an x to the 5 and an x to the 5, and if those were also the same power, like y to the 7, y to the 7, then we would see that. When they're not, right, we have x to the second x, and then we have y to the first, y to the third. You can't expect that to happen. You'll see that because you're gonna have a ton of these. And try to remember that everything you're doing for homework tonight, really, the point is to become so familiar with these that when we go to do the opposite, you do something like, oh, I've seen this before. I know what this, I've seen this type of thing before. I know what this is going to look like. Now, something like this, that's just terrible. And we're normally not going to be going from this to this, but you will absolutely be, oh boy, we're just going to go ahead and do it. So your book calls this no, it just calls it squaring a binomial. This is called a perfect square. When you have, we're going to use x and y, and we're going to say, okay, if I do that, if I square that, and I'll leave this up here. Well, this says, now there's a formula for it, but honestly, I think it's harder to remember the formula than to just do this and then FOIL it out. What do I get when I FOIL it out? What's the first?
X squared.
X squared. What's the outside?
XY.
XY. What's the inside?
YX.
Or
XY.
What's the last?
Y squared.
And then we notice, can I combine those?
Yes.
And what do I get when I do?
2xy.
Plus 2xy plus y squared. And so this is the form of a perfect square. Right? It's some value squared plus 2 times whatever that value times that value is, and then the last value squared. And just real quick, like, so if I had something like this, if I had, say, 3x plus y squared squared. What I could do is say, well, wait a second. That first thing, whatever it is going to go into this formula right here. And basically now I'm just plugging things into a formula. Say the first thing goes in wherever I see the first thing was. And so when it's, see what we're doing here, right? We're trying to compute this value, 3x plus y squared quantity squared. We could say, oh, that's a perfect square. So I square that, I plug in 3x. Okay, we have an x there. So that was the first thing here, right? That's what we took in the beginning. And so we're going to say, okay, 3x goes here. Then the second thing, I'm sorry, this is confusing. I probably should have used A's and B's to get this, and then, or maybe use A's and B's over here, but you see what
this makes sense.
It makes sense. Okay. So then like the second thing in this case was a y squared. Okay. And then the last thing that we had is a y squared. And so we get this, in which case now I've plugged it into a formula. And now I could go through and say, well, 3x times 3x is 9x squared. And then 2 times 3 is 6. X and y squared, those don't mix more than that right there. And then y squared is y to the 4th. Could do it that way. Or what I would do is just FOIL it out. I'm going to say, okay, 3x plus y squared squared. And by the 10th one of these that you've done, this step that I'm taking right now, writing it down like this, you won't have to do anymore. Like you'll get it. You'll be able to just see it in your brain. Like when I look at that, I can imagine a copy of that right next to it and then go first, outer, inner, last. But my point here is formulas suck. Like I hate using formulas. I'd rather just say, what does that mean? That means that. What is that? Oh, that's a binomial and a binomial. Oh, I have to FOIL that out. Okay. So you do it. What's first?
6x squared.
What's 3 times 3?
Oh, 9x squared.
There we go. 9x squared. Outer gives me what?
1 3x plus y.
Say again. Oh.
Sorry, I was writing it down.
Okay.
3x y squared.
There we go. So plus 3xy squared. What about the inside?
3xy.
Oh, wait.
Oh, I didn't see those. Yeah. So 3xy squared.
Oh, it gives you the exact same thing as you did with the outside. Huh, interesting. It kind of has to, right?
Yeah.
You're squaring it, right? And you'll notice it, and this is why you're going to get a bunch of these to do, is that after doing it about 15 times, it finally goes into your head like, dude, I know it's a perfect square. I know I'm going to be adding exactly that to itself. It's going to be 2 times as much as that. But anyway, okay. So we did the first, we did the outer, we did the inner. Now let's do the last. What does the last give me?
Y to the 4th.
Y to the 4th. And now can I combine any of these terms?
Yes. You can combine the middle two.
Uh-huh. And what do we get?
6xy squared.
All right. And then I'm just going to drop this down. We get 9x squared plus y to the 4th right there. And we get exactly the same thing as if we plugged it into a formula, but in this case, we didn't need to use a formula. And it'll be, after doing about 20 of these, you'll be faster doing it this way than you would plugging it into a formula. I suggest to just do this every time. So there is a formula in there, and it's good to know that, yeah, no matter what goes in there. And this is, can I erase this stuff?
Yes.
Okay, so it's good to know that the formula says a plus b squared is equal to whatever a is squared plus 2ab plus b squared. It's good to know that, right? That is the case. Sometimes that will be helpful for us. But to try to, if you're given one and you're trying to actually compute it, like if I give you something like this and say, tell me what that is, it'll be easier to just FOIL it out than it would be to memorize this. But it is good to know. It is good to know. Now, there's one thing I'd like to talk about real quick is what happens when there's a minus sign in between it. So let's go 2x minus 3y quantity squared. So I'm going to say, all right, well, this is something squared. Let's first outer interlast this guy. So what do I get for first?
4x squared.
4x squared. Outside.
Minus 6xy.
Minus 6xy. Inside.
Minus 6xy.
Minus 6xy. And last.
Minus 9y squared.
What's negative 3 times negative 3?
Oh, 9.
Plus
9y squared.
9y squared. This is why I wanted to do this, because there's something
Ay.
that happens. It's almost exactly the same formula. The only difference when you have a negative in between them and when you have a positive is that this term is negative. Because if you think about it, right, you're squaring something. You're taking something, it doesn't matter if it's negative or positive. You're multiplying it by itself. It's got to come out to be positive. When you do this, that's going to be a negative and a positive and a negative and a positive. They're both going to be negative. And I'm just going to go ahead and cut to the chase, combine these guys together, minus 12xy plus 9y squared. That is going to end up being negative because you have opposite signs in there, right? So when you multiply the outside and the inside, you get a negative. Multiply the inside and the outside, well, it's the exact same thing, and it's still negative, and therefore you have two of them. In other words, negative 6 plus negative 6 is 2 times negative 6. And then it just happens to be a negative number. And then with the last, I don't care what it is, it's a negative, it's whether it's a positive number, a positive times a positive is a positive. But if it's negative, well, it's a negative times a negative. So it's also a positive. And so that, and I think, again, this is way easier than trying to use a formula and then memorizing 2 separate formulas for either a plus b or a minus b. Just do it. It's easy. And you have the added benefit of after doing 1,000 of these, when we go to factor, this will be easier to recognize. When you get something like this and it says factor it, in other words, undo this thing, you'll look at it and go, man, that looks like something squared.
Yeah.
That looks like something squared. Hey, that looks like 2 times something. And there's a negative there. So I know that there must be a negative there. And so we'll get there. But this has the added benefit of being able, like getting this in your brain is really good. Okay.
Yeah.
Okay. We're at 11 o'clock. There's not too much more I want to say. But I do want to go on. Do you still have time? We still good?
Yeah.
Okay. So there are, when we have a sum and a difference, there's an interesting thing that happens. So they give you yet another formula and say that when you have a plus b times a minus b, you get a squared minus b squared. Why is that? Well, let's first outer interlast this guy. What's that times that?
A squared.
A squared. What is the outside?
A minus AB.
Minus AB, right? Because you have a positive, and whenever you're doing these, look at the coefficients first, right? And when they're not there, it means they're 1. And so it's like I have a positive 1 and a negative 1. Positive 1, negative 1 is a negative 1. And then I have my variables, which are AB. Okay, so A and B. What about the inside? What do I get from my inside multiplication?
Plus AB.
Plus AB. Oh, hey, it's the opposite of that. Okay. Now what do I get with the last?
Negative b squared.
Negative b squared. It has to be negative because here you have a positive and you have a negative, making it a negative, then b squared. These guys cancel out and you get a squared minus b squared. And that's where the formula comes from. It comes from actually foiling this guy out. And so now what's nice about this is that if you recognize that you're in this scenario, you could just jump to the chase and do this. But in my head, like this is how I like to think about this. If I have a 3x squared, how about plus 4y? Let's do a 4y. And then I look at this and go, I'm given this. First thing I notice is, hey, whoa, hold up. These are opposite signs. And so I should end up with something canceling out. But then I just go ahead and do it and say, okay, first, outer, inner, last. What's the first?
9x to the 4th.
There you go. Outside is, and now this is where I notice, that multiplication is going to be the same as that multiplication. The only difference is that that one's negative. I'm going to have a negative, and then I'm going to have a positive of it. It's going to cancel out. But we'll just go through and do it. What is the outer when I do the outer?
Minus 4x squared y. Minus 12. Sorry.
Minus 12x squared y. Good. What about the inner?
12x squared y.
Hey, they cancel out. Look at that. Now, what about last?
Negative 16 y squared.
There you go. And we can see, yep, those cancel out. And so we have 9x to the 4th minus 16y squared, which matches with what we said. You take, when they have the opposite signs in them, it's exactly the same, except for the signs are different. It's always going to work out that the outer and the inner are going to cancel each other out. It has to be that way. I don't care if I put a smiley face and a frowny face, smiley face minus a frowny face. The outer inner are going to cancel each other out, and you're going to be left with. And so you'll get to a point where you recognize that and you go, oh, that's the same thing as if I just squared that guy, and that would give me, that times itself would be a 9x to the 4th minus, has to be minus, that thing squared, which is 4 times 4, which is 16y times y is y squared. But I think it's still good to just do it a bunch of times as well. It's, and it, you know, so to just actually foil it out so that you believe it. And trust me, they don't make it, they don't say this, but the more that you do this, the more that you have, that you've in your head said first, written something down, outer, written something down, inner, written something down, last, the better you're going to be at factoring, which is really what all this is about. Like, so, okay, we did that. Now, oh boy, this is where it's going to get fun. And I really want to do, I don't want, okay. We're going to go a little bit beyond what the book has. If you're overwhelmed by what we're about to do, just drop it. But okay. I want to give you something that's going to make your life so much easier if you want to roll with it. So we're gonna do something. Okay. So we're going to use X's and Y's. But in principle, this could be anything. It could be an A and a B. It could be a 3x squared and a 5y to the 7th, right? It could be, it's just that whatever goes here is one number. Whatever goes here is a different number. They might have mixed variables. They might not, but we're just going to rewrite whatever it is as x plus y. And let's start off with this. What is that if I raise it to the 0 power?
X plus y.
To the 0? What is any number?
Well, isn't it? Any number raised to 0 is 1, right?
Yes. It's a good. Any number any number raised to the 0 power is equal to 1. Okay, so in other words, this is when my power, right? When my
Mhm.
power is 0. So think about it like this. We're gonna do this right because why not? So when n is 0, then this thing, x plus y to the n, when n is equal to 0, the whole thing comes out to 1. Okay. Okay, there we go. Now, what is it when it's raised to the 1?
X, Y.
X plus y, yes. Yeah, that's a tricky one. But yes, it's just x plus y. And so what I'm going to do here in this column, I'm just gonna keep track of the coefficients. Okay. So what's in front of the x?
A 1.
A 1. What's in front of the y?
A 1.
Okay. So a 1 and a 1. Now, here we go. X plus y squared. Don't memorize it. We're just going to work it out. We're going to say, okay, x plus y times x plus y is what?
X squared. X, Y, X, Y. 2xy, I guess.
And
And then y squared.
Y squared. Okay, so let's see. X squared, you already said 2xy plus y squared. So what are my coefficients?
1, 2, and 1.
Okay. 1, 2.
Oh,
Oh.
I remember doing this.
Oh, yeah. So, all right, let's do one more. One more. What happens when I raise this to the 3rd power? And now I have x times what? I mean, x plus y times x plus y times x plus y. What I'm going to do is use what we just found out, right? When I first outer inner last this guy, I end up with x plus y. Now I'm going to go ahead and rewrite this. So first is x squared. Outside is xy, inside is xy, and so I get 2 of them, 2 xy's. Finally, y times y is y squared. Now this is where I'm going to do my double distribution, right? I'm going to go, okay, the x jumps over and hits the x. I really wanted to get into this example because I want to show you a good way of doing this. Now, you'll notice the first polynomial is in the order xy. The second polynomial is in the order of descending values of x, right? We have x squared, x to the first, x to the 0. When you are in that scenario, something's always going to work out if you do it the way that I'm about to do it. So I'm going to do the x's first. I'm going to multiply that x into that x. And what do I get when I do that? X times x squared is
X to the 3rd.
X to the 3rd. Now I'm going to distribute over and go into there. What do I get? What's x times 2xy?
2x squared y.
2x squared y. Plus, now I'm going to do the last one. I get
X y squared.
Y squared. Here's the nice thing. Since I've done that, and it's pretty obvious to see, x's are still in descending order, right? Because I've started with x's in descending order. I've basically just thrown one more x into the mix, and now we still have x's in descending order. Okay. Now, let's throw the y in. So the y needs to distribute into every one of these. So the y multiplies the x squared, and I get what?
X squared y.
X squared y. And look, I already have a column of x squared y. So I'm not going to write it over here. I'm going to say, oh, cheers, 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 cheers. He likes to cheers now. This is his new.
Aww.
Yeah. Just a minute, buddy. Just a minute. So Okay, x squared y, I'm going to drop it into the column with the other x squared y's. You'll notice it's 1 over from the previous one. That's kind of confusing. So now I'm going to distribute the y into the next one, and what do I get?
2xy squared.
2xy squared. Oh, look, it's the next column over. It has the same thing. So 2xy squared. Okay. Finally, the y goes all the way over into the last and gives me what?
Y to the third.
Y to the third. And now I add these bad boys up and I get, now because I've chosen to do it this way, and I will do this, this is the way I will do this with any two polynomials that are bigger than just a 2 and a 2. Anytime I have something bigger than a 2 and a 2, this is the method that I use. And as I'm doing it, I take my first thing, multiply it through to get a row. And then as I do the next one, I just ask myself, okay, I did that times that. Do I already have those somewhere? Oh yeah, I already have those right here. So I'm going to put that one under it. Now it might not work out that way if this isn't exactly 1x and 1y. It might show up later on or something like that. It might not be this nice. But this is a good way of keeping yourself organized, because the bigger these get, the crazier it gets. And so basically, as I do this second row, I'm thinking, well, I could put this anywhere to add it together. Why don't I put it in the column of the other stuff? Does that make sense?
Mm-hmm.
Okay. So I get 1x to the third plus what? Peter, please.
3x squared y
3x squared y plus what?
plus 3xy squared
3xy squared plus,
y to the third.
what are my coefficients? What's the first coefficient?
1, 3, 3, 1.
Huh. This, have you ever heard of Pascal's triangle?
I have.
That is what this is. And you'll notice that, like, what we're doing here is each new row. Okay, so this is when n was 2. This is when n was 3. Each new row is obtained in the following way. We could have, without looking at this, we could have obtained this row by saying, well, there's always a 1 to start off. So we have a row, the next row gets a 1 in the front. Then we add those two numbers together. What's 1 plus 2?
3.
Okay, now we add those two numbers together, and what do we get?
3.
3, because 2 plus 1 is 3. And then it finishes off with one row.
Mm-hmm.
Sorry, with a 1. And we can see what did we just do here? We said from the first coefficient and the second coefficient. Well, look at that. That was from the first coefficient, right? This guy came from, or not, so that's the second coefficient. This guy was the first coefficient. He came along when we brought in another y. The second coefficient was from that term, and he came in when we brought the x. Ditto over here. The second and the first coefficient give us that guy, and we could see that that guy comes from, well, the second coefficient comes from when we had this guy, and then we brought in another y. This guy came from the the last coefficient, and it was what happened when we brought in another x. And that's kind of why this all works out. The extra one that we get comes from the fact that, well, that y is going to bring that one y up by 1 power to give us that.
Mm-hmm.
Notice another thing, because I've written it in this special way, we have descending orders of x's, and we have ascending orders of y's. So using this information, what I could do is say, well, if it's 4, here you go, buddy. Here you go. Here's your cup. Yay, cup. What I could do is, instead of doing all of this, which I'm sorry, but we're going to do, I could just say, well, hold up. 4. What goes on the very outside here?
1.
A 1. So then what goes here?
4.
4. Then what goes here?
6,
Then,
4,
and then
1.
a 1. And I could say, well, if those are the coefficients, and I know I have descending powers of x, then it should start with x to the 4th, right? Because that makes sense, right? We know that the outside thing, I don't care how big this gets, you have 1x right there, and you're just multiplying by another one of these guys, then you have to have 1x to whatever, that's your x value. It has to be raised to the 4th power. So I know that it's got to be x to the 4th, x to the 3rd, x squared, x, and then 0 x's, or x to the 0 is the number 1. I know I have ascending powers of y, so no y's, 1y, 2y's, 3y's, 4y's, and now it's just the coefficients. I know I have 1 of those bad boys, 4 of those, 6 of those, 4 of those, 1 of those. They're all pluses. And that's a nifty formula. That's a or it's not even a formula, it's a nifty little device you could use to compute x plus y to the 4th. And we could verify this if we wanted. We could say x times y to the 4th is just the same thing you get when you get this, but you multiply it by 1 more of these guys. I'm not going to go through that, but you could see that, well, that's exactly what we've just done here. The x is going to get there. So x times x to the 3rd will give me my x to the 4th. There's only 1 of them. Jump over here. That brings all the x's up by 1. And so you'll have 3, 3, 1. Bringing the y's over kind of shifts it the same way we did before. And then you're adding the same way that we were adding before. And you would get this right there. So that's a nifty little thing to have right there. Really, we're probably never going to talk about anything below this line. You might see one of these. I don't think there's any to the 4th power in your homework, okay. But you're definitely going to see this. So this is a good one to be able to do right here. And one more thing about that to notice is that if you change the negative, if you make this an x minus y, let's do that real quick. I want to get this out of the way. So if we had, instead of x plus y, so we know that this is, because we just derived it, we know that that's the same as x plus y to the 3rd. But if we had x minus y to the 3rd, we could say, well, if I need a minus there, I could rewrite this thing as x plus negative y. It's a nifty little trick to use whenever you're dealing with, well, with math. And you say something minus something is the same as plus a negative. And now you could say, well, wait a second. So everywhere that I see a y, I'm just going to replace it with a negative y. So I could go through and say, so basically what I'm doing here is saying x plus negative y to the 3rd is equal to, and so x cubed does not change, plus 3x squared, and I'll deal with that in a second, 3x whatever squared plus that cubed. And now instead of a y, we're just plugging in a negative y. And so I go, okay, that's the same as negative y, negative y, negative y. And then I remember from our discussion last time, a negative raised to an even power is positive. Mm-hmm. A negative raised to an odd power is negative. And so I'm going to say wherever I have odd powers, I'm going to pull out the negative, x cubed. So that is an odd power of y. So we pull it out as a minus 3x squared y. That's a even power of a negative, which stays positive. So plus 3xy squared. Negative to an odd power stays negative. So negative y cubed. And you can see that when you have a minus in here instead of a plus, you have the exact same coefficients. The only difference is all the odds, or we could think about it as every other one is even or is negative, positive, and that just goes on forever. That will work with any one of these rows. Oh, buddy, yeah, I gotta give you a hug. And so if you were like to the fifth, you'd say, well, 1, 5, 10, 10, 5, 1, like that. And so if you had, say, x minus y to the fifth power, you could use those coefficients and say, oh, it's a minus. And so I call it a blinker. It blinks. It goes off, on, right? You'll know like that'll do the same thing, but it's ultimately the same formula. It's one of the few times that I think of being able to use a formula because it actually makes your life a little bit easier. They usually add too much needless complication. In this case, way easier to just draw Pascal's triangle down to the fifth row and then say, yeah, those are the coefficients right there, and then plug it in and do all that. But like I said, we're not going to be we probably won't deal with anything down here, but you're definitely going to see stuff cubed. So it's nifty to be able to do that. Yeah, so are we good to go? Okay, real quick, let's see. So we need to give you homework for today. And I got that. I think there was one I wanted to talk about. Okay, so you got a lot of them are something squared. I would suggest to FOIL it out, write it like it'll be something like 5x plus 2y squared, 5x plus 2y, quantity squared. I'd say in this homework, later on, you do whatever, but for this homework, go ahead and write it like this. That should be your first step, and then just FOIL it out. And say in your head, first, outer, inner, last, as you're doing it. There was one I wanted to do real quick. I wanted to do number 2 as an example. Yes. Okay, so number 2, it says, okay, am I good to erase all of this?
Yes.
Says multiply, and it gives you 2x. Oh, that's not the one I wanted. Oh, that's the one I wanted. Okay, 3y squared. 3y squared minus 3y plus 9. 2y plus 3. Very similar to the thing we just did, right? Where I had descending powers, and then I also had descending powers of y, okay? So what I like to do is I put my smaller thing on the left-hand side, and I put my bigger thing on the right-hand side. This helps me just keeping things organized. Because like I showed you before, as I start to stack up the stuff, it's really nice to be able to stack it up right beneath it. And I'm not worried about, the book does something so stupid. It's like the first example they do, they go ahead. I don't even want to get into it. It's the way I like to do it, right? I'm going to put the smaller thing on the left, the bigger thing on the right. I'm going to make sure that I have descending powers of both. So y to the first, y to the 0, good. Y to the second, y to the first, y to the 0, good. Now, double distribute. So I'm going to start with the left one. I'm going to start with the big power and go big, second big, third big. And so what is 2y times 3y squared?
xy to the third.
What's that?
It's not x, 6y to the third.
6y to the third.
Agree.
Okay, now what is the second one? 2y times negative 3y.
Minus x to the second.
Say again?
Minus x to the second. Xy to the second. My gosh.
Minus 6y squared. Yes.
Yes.
Now, the last one. He's distributed all the way over to here. And what do we get?
18y.
18y. There we go. Okay. Now, okay, I'm going to do the other one. I'm going to take the second term and distribute him into each one of these terms. And so what do I get with this first one?
9y squared. 9y squared.
9y squared. Which column should I put this in?
Under the negative xy squared. The second column.
There you go, right? Like we want to keep the types of things the same. So I'm going to go 9y squared. Okay, so now I distribute over and get what?
Minus 9y.
Minus 9y. Oh, and look, it's already in the, that's the great thing about having descending powers, because really you could guarantee that the next thing is going to match up. Okay, so then now what's that last one?
27.
Plus 27. There we go. Now I'm going to take those and add them all together. 6y cubed is just 6y cubed. Now what do I get here?
3y squared.
Plus 3y squared. What about here?
9y plus 9y. And 27.
7, and that is the answer. So again, whenever you're doing these, I prefer to do it this way. You could have done it in the opposite order, but it's nice to be able to write directly under here. You know, I don't know, it just helps me organize stuff because I see, oh, that times that gives me that. That times that gives me that. That times that gives me that. That way, if I go back and check my work and say, uh-oh, I got something wrong. Where did I go wrong? It's easy to kind of look back and see, well, this came from there, that came from there, that came from there, and so on and so forth. Also, I don't think I need to stress that anymore. That's super nice to do it that way and to have it written one under the other, make your life way easier. So, good to go?
Yeah.
All right. Okay. Now, homework. So we are in chapter 5, section 3. Five, 3. This is page 217 through 18, I believe. 19. Okay. So. One, 5, 9, 11, 13, 15, 17, 19, 21. Three, 27. 29, 35, 37. Yeah, 42. That one's fun. And 46. Oh, 46. Oh, man. Okay. On 46, there's a very hard way of doing it. And then there's a much easier way. And here's the hint for 46. Okay. If I have two numbers, say a raised to a power, let's just say it's a raised to the third. And I multiply that by some number b raised to the third. Okay, so this was your hint. It was that if I have some number a raised to the third times some number b raised to the third, I could say, well, a to the third is a times a, and b to the third is b times b times b. And I could compute it that way. I could say, okay, I could take a times a, figure out what that is, b times b times b, figure out what that is, then multiply them together. Or I could say, well, wait a second, this is all just multiplication. I could do multiplication in any order that I want. I could basically bring this b over to here and go a times b first. Then I could bring this b over to here and go a times b. And then I could bring this b over to here and go a times b. It's exactly the same thing, right? It's 2 times 2 times 2 times 3 times 3 times 3 is the same thing as 2 times 3 times 2 times 3 times 2 times 3, right? And so we could rearrange it basically and rewrite it like this. So one of these ways is going to be ridiculously hard to do. The other way is going to be much easier.